Welcome everyone to this class. Today also we are continuing with heat conduction. Some of the topics that are uh, taught in this third week of the course regarding the heat conduction, which includes uh, lumped uh, conduction or lumped heat transfer problem. We'll take some numericals about that, and one thing that was not taught in the class that also I'll discuss, that total heat, how you calculate total heat loss from the body. Second is regarding the 2D steady state heat conduction. Uh, then, like, there are different cases in that, uh, and apart from that, there will be brief discussion about uh, similarity solution for 1D heat conduction in semi-infinite domain. Uh, then, yeah, in last class we finished with the uh, fins, various type of fins and their formula, etc. But we could not take any problems. So we'll start with the fins. We'll take some problems. Then lumped capacitance uh, or lumped heat conduction in this case. And then 2D heat conduction. I will give you a brief outline as to how you do it. And I mean, it was taught in class also, but I'll take maybe a general, uh, you know, general this thing. What you say? General case, and we'll derive it. Actually, first of all, it's a separation of variables, but depending on the boundary conditions, the eigenvalues or the coefficients of those sine and cos term change, uh, and the constants that again are function of boundary conditions. They are also you have to use some orthogonality principle to get that values. And then in case of 1D semi-infinite domain heat conduction, so basically it is a similarity solution method. Uh, we may not do it thoroughly here. I mean, whatever is relevant for conduction we'll discuss, but in case of boundary layer also, it will be there. So maybe we can discuss it there. Uh, but yeah, uh, okay, we'll talk about it when we come there. Basically, you should know when to use similarity solution method. It's not specified to only semi-infinite heat conduction. In any case, if there is a semi-infinite or infinite domain or one length direction, you cannot, uh, quantify or measure. So in that case, people generally use similarity solution. We'll talk about it sometime later in the class. So let's start with some problems on heat. You know, uh, fins. So basically, in class, sir has derived the formula for that when you have fin surface, when you have number of fins on a particular base surface, and there are like number of fins, and you need to calculate the overall surface efficiency for heat conduction, and that type of problem will take. So, and that derivation sir has already done in the class. We'll use that directly, but you should know that how to do that. And maybe you can go back and check your class notes. So let's see. So this problem is so. So we are, because we already discussed the formulas in the last class, I'll not be going there. Uh, so we'll take first question. I'm not taking the simple questions, like uh, directly you have to use the formula and calculate the temperature at the distance for some type of fin. So those you can do. We'll take slightly uh, complicated one here. So okay, you have a base plate, something like this, and actually it's a square cross sectional area, so maybe I should draw it properly. So it's a square plate or base plate as in terms of in methodology. And I'm not drawing the 3D one, I'm just giving you the so this is 20 mm by 20 mm plate, uh, and one second. Okay, so this plate is soldered to a aluminium heat sink of thickness 3 mm. So here you have one okay, I'll draw the figure directly. And so this will be same in the third direction. So okay, so you have fins like this. I'm not drawing all of them because it will take a lot of time, but you get the idea, right? So fins are like this. I'm just indicating a break here. This means that uh, you know there are like multiple fins. Don't worry about those, and they are you can show them like this. So this thickness is given as 3 mm. So basically, you should understand that these are two different components and they are soldered together. So there will be a base plate, and there is a soldering that is done here. Uh, Maybe I can show that also directly so that you understand it. So okay, maybe you can show it like this. Uh, hmm. Yeah. So this is your base plate, and this is your aluminium fin structure. Okay, so these are two things, and they are soldered together. This is 20 mm, 20 mm. Yeah, and the thickness is 3 mm. Length of each fin is given as 15 mm, and through these channels the air flows which is at T infinity, I mean bulk temperature of air is around 20 degrees Celsius, and the convective heat transfer coefficient is given as 100 watt per meter square Kelvin. And fin spacing is of about 1.8 mm, and number of fins are 11. Fin thickness is 0.182 mm. And fin pitch. So pitch indicates the gap between two fins is 1.982 mm. Okay. And the solder joint between the base plate and the aluminum fin structure has thermal resistance of 2 into 10 to the power minus 6 meter square Kelvin per watt. Okay, and you need to find, it's a two-part question. If maximum allowable base plate temperature is 85 degrees Celsius, what is the overall surface efficiency? So basically, what is the overall if surface efficiency due to fins? They have not mentioned explicitly, but this is what they are asking. And second part of the question is okay, we'll deal with the second part later, because otherwise it will become too lengthy of a question. So this is actually, this was like a complete half-page question. I just gave you the important things that are important for the problem. So now you need to go back to the class lecture and find. So this will be like this. So these fins will be, along the length. So I mean, maybe I can show it using some lighter. Yeah, so these fins will be not like, in reality they'll be like this. Okay. I just don't want to complicate the figures. That's why I'm using different color. So now we know the, you know, so base plate area is nothing but 20 cross 20 mm square. So that is the base plate area, right? So that comes out to be 400 mm square. So 400 into 10 to the power minus 9. So that will be 4 into 10 to the power 7 minus 7 meter square. Oh, no. It's mm square. So 6. So 6 minus 2, it will be 4. So it will be 4. But out of this area, what is the area available for heat transfer from the base? So base plate area available for heat transfer. So that will be total area minus, let's say if I call it as AB. So that will be total area let's say AB prime, total area minus fin area, right? So that will be minus n is the number of fins into uh, the length of the fins into thickness. So basically this will be thickness of the fin, one fin into width of the one fin. So this 20 mm is nothing but the width for the fin, or the length also you can call it, but you should be consistent. So now we know there are 11 fins, we know the thickness of each fin, and we know the width, which is along that 20 mm direction. So if we do those calculations, you should get, let's say we'll call this as base plate area for heat transfer. We should get 3.6 into 10 to the power minus 4. I'm not doing the calculation because it will take a lot of time. You can verify the answers later. Now that is one. And now what is the heat transfer surface area offered by fins? Let's say AF. That will be, you neglect the, this thing. The, you can assume, if nothing is mentioned, you can typically assume that it is a adiabatic fin. So, let's, if you take one fin like this, so this is one fin, right? So this direction is nothing but this length is, let's say the fins are like this. Okay, so this dimension is 20 mm and this is 15 mm. Correct, no? So and you neglect the heat transfer from this area. You neglect those because they are very thin, and also from the bottom you can neglect those. So basically major heat transfer is happening through this area and same area on the back side. So that will be uh, number of fins into 2 into the width, which is 20, and the length of the fin, which is given as this is your length of the fin. Okay, so this will be your LF. So now that is nothing but it will be 66 into 10 to the power minus 4 meter square. I'm not doing the calculation because it's pretty much straightforward, and I have done this previously. I mean, not here but earlier. 1 second. 2WLF. So width is 20, LF is, so that will be 3 into 2, 6 into 11, 66. Yeah, it should be correct. Okay. So now total heat transfer area, that will be your AT, will be nothing but AF plus AB. So similar derivation is already done in the class, so you should understand what is going on here. And if you do the summation, here it will be 69.6 into 10 to the power minus 4 meter square. Okay, so that is one. Now we know the formula for overall efficiency. Overall efficiency, okay, is given as 1 minus n AF divided by AT total area into 1 minus fin efficiency. So we know AF here, and we know actually since we are multiplying by n in the AF, we should not write n here. So it should be like that. Okay, and we don't know the efficiency, fin efficiency. So assuming adiabatic fin tip, fin efficiency is given as tan ml divided by mlf. So length of the fin we know, m is unknown here. M we can calculate. M is given as usually the formula is under root hp by ka. So here perimeter will be you know 20 plus the thickness of the fin, which is 0.182 divided by actually I should not add here, let's say because we can further simplify it, and that is typically done in many cases. So perimeter here is nothing but 2 into uh, the width of the fin here into fin thickness divided by k into area. Area will be again w into t, and this will be plus. So what happens, since w is very much greater than thickness, because we know that w is 20 mm and thickness is 0.182 mm. So this is correct, this is valid argument here. W plus t approximately becomes equal to w, and then you can cancel w in the under root square sign, and then you're left with 2h by kt. And if you do this calculation, you should get something around 78, because you know h, you know k. K did I mention? Okay. So K for aluminium will be high, and the exact value is nothing but 180 watt per meter square Kelvin, and that is the reason why we put aluminium fins, or it should be meter Kelvin, because they offer high thermal conductivity. And then you calculate the fin efficiency as using the formula given above, 10 HML by ml, and you'll get 0.704 as the fin efficiency. Now we put back into the overall efficiency formula, and you should get 0.719 or 71.9%, whichever unit you want to use, you can use. So this is your answer. So here the important thing is you should know or remember this formula. If you don't, then it will be very tough to solve the question. And this derivation is done in the class by professor, so you can refer to that. Now the second part of the question, which is what is the value of maximum power that can be transmitted through base plate. So basically they have mentioned that the base plate temperature cannot exceed 85 degrees. It was mentioned here. So now they are asking what is the maximum power that can be transferred. So basically that maximum power will be achieved when the base plate is at 85, right? So that is the case here. So now and they have given one hint here, so that so instead of doing the hard way, they have provided a hint here. Effective fin thermal resistance RF is given as 1 by overall efficiency H and total area. So that is the case also, because we write Q as some fin efficiency, overall fin efficiency, into HA, total surface area for heat transfer, into delta T. And this is equivalent in terms of the thermal resistance network architecture, where you have Q delta T by R thermal resistance for fins. If you if you compare these two equations, you will end up with the thermal resistance formula, which is nothing but in this form, which is also the question has given the hint, but even if it is not given, you should know that this is the overall resistance for fins. Okay. So now see your base plate temperature maximum is 85 degrees. Then there is solder. I'll call it RS. So this is soldering resistance, which is given in the question as what is it? 2 to the power 2 into 10 to the power minus 6 meter square Kelvin by watt. Then your base plate starts and it has 3 mm thickness. So another thermal resistance will come in this network. So this is your base plate. Not base plate, sorry. This is your aluminum plate thickness. So this is, we have this formula, B by Ka. This is, the plain simple wall formula. So this thermal resistance is nothing but in this part. So this is the part where you will have conduction resistance, right? So that is what we are representing here using this. So we had thickness of this part as 3 mm given in the question. Conductivity is 180, and area, it's nothing but again that square cross sectional area, right? 20 into 20. So it will be 400, or directly I can write 4 into 10 to the power minus 4. So if you simplify this further, you'll get 0.042 Kelvin per watt. Yeah, so now here the unit is meter square Kelvin per watt, and here we are getting Kelvin. So we have to divide this by area. Therefore, so that we will get Kelvin by watt. That is the standard unit for uh, thermal resistance. So to do that, what we'll do, we'll divide this by the base plate area. So that is 4 into 10 to the power minus 4. So if you do that, you get 0.005 Kelvin per watt. So these units should be, consistent. That's why we are doing these things. And then you'll have the fin, the thermal resistance offered by fin, and that will be nothing but 1 by overall efficiency, total heat transfer area, and H. Overall efficiency we just calculated, 0.719. Total area for heat transfer we have as 69.6 into 10 to the power minus 4 into H, I think is around 100. Yeah, H was I think 100 only. Yes. So if you simplify, or you can do the calculations further, you should get this value approximately 2. Yeah, it should be, because this minus 2, minus 4 and 100 gives you minus 2. So this will become 0.7. So 0.7 is 0.49. So 1 divided by 0.49, it should be around 2. And then you have the ambient temperature, which is T infinity, which is given as 20 degrees. So this is your whole thermal resistance network. And then you can calculate Qmax as Tmax minus T infinity divided by total resistance Rs, Ra plus Rf. And this will be 85 minus 20. And this will be, I think, around 2 plus 0.042 plus 0.005. And therefore, maximum permissible power allowed to transfer without crossing the 85 degrees limit should be around 31.8 watts. So one can verify the calculations, and we should arrive at this point. So this is the typical question that is asked from fins. Apart from those what you say, uh, those single fin question, this is like the whole fin assembly question. We can take one more question. Uh, this was slightly different type of question. Okay, 1 second. I'll just confirm the question. Yeah, and actually, okay, we'll solve this question and then we'll come back to this observation also. Okay, so question is, here you have a steel pipe. Okay, and it's a long pipe, something like this. Okay, and there are sorry, there are annular fins on this cylinder, and they are 8 in numbers. I'm not drawing them perfectly, but you get the idea, right? They are same type of fins, not their length and width and thickness are also same. In this figure, it may not look like it, but forgive me for my bad drawing. But there are like eight of these fins, and I'm not drawing it, but they go in this direction. Sorry, they are in this direction. So 8 of them will be like annular fins. You understand, right? So this is the case that we have. Uh, the length of each fin is 30 mm. Thickness of the fin is around 1.5 mm each for a single fin. K for the thin material is given as 45 watt per meter Kelvin. And heat transfer coefficient is given as 75 watt per meter square. They have not mentioned length in question. Okay. I mean length of the pipe. And they are asking, we need to find the increase in rate of heat transfer due to addition of fins to pipe surface. So how much more heat you are getting? They have not mentioned any length of the pipe, any temperature limits here. So we have to assume unit length and some delta T, which is constant. So let's say this pipe is at some base temperature TB and you have some T infinity as your ambient temperature. Now, first thing, if there are no fins, then what happens? If there are no fins, yeah, and okay, they have mentioned the uh, pipe diameter of 8.9 centimeter. So diameter they have given, but length is not mentioned. Okay. So if there are no fins on the pipe, Q without fins will be HA, your base temperature of pipe minus infinity. Correct, no? And what will be this area? It will be H into pi d L dB minus T infinity. Assume L as 1 because they have not mentioned L as any quantity is not given for L in the question. So here you can assume L as 1 and therefore you'll get Q which is watt per meter in that case, So that is per meter heat transfer. So this will become pi H D TB minus T infinity. TB minus T infinity is also unknown, so uh, you know you can keep it as constant. Let's say we'll keep it as constant as theta b, and we'll assume same for fins. So basically, your and if you multiply this pi into d into h is given as 75, d is 8.9 centimeter, pi is also 3.147. You should get 20.97 into theta b. Theta b is unknown, so let it be. So this is your equation 1. Now, uh, with the addition of fins, what happens? So the story goes similar to the previous question. So so this is your first case, and let's say second case with fin addition. What happens? First of all, you have to calculate area again, right? So uh, what will be your base area, which is uh, surface area of the pipe without fins. So that will be again surface area is pi d pi dl minus, you have to subtract those. So this is pi dl is the total area that you have for a pipe outer surface, and then you have to multiply number of fins with the fin thickness, right? Fin thickness into length. So this will be your uh, base area available for heat transfer where fins are not there. L is 1, so this effectively becomes pi into 0.089 minus number of fins are 8, and each fin has thickness of, I think, 1.5. Yeah, 1.5 mm, 10 to the power minus 3. So if you do this calculation, uh, 1 second, I'll just do it because I don't have the number. The number is there for final answer, but anyway, we'll do this. Pi into 0.089 minus 1.8 into 1.5 into 8, that is 12. 12 into 10 to the power minus 3 minus 0.000, no, sorry, 0.12. Yeah, so this is 0.268 meter square. Okay. Yeah, I think it is correct. 15.6. Okay, so this is your area without fins. Now what is your fin? I am using same nomenclature. Okay, so AB in the last question we used for base plate area for heat transfer without fins, and now fin surface area is again same, N into 2 into W into LF. So that will be uh, number of fins into what should be 1 second. See, here we can do it in simple fashion only. We need not to do all these things. 1 second. So we can calculate heat from base without, I mean, you understand my point, right? Without having Q from base where fins are not present. So that will be HAB into theta B, right? So we have area, we have HS 75. So that will be into 75. So this will be 20.07 into theta B. Okay, so this is the second data you have. Now you need to know the heat transfer from the fin, how much heat you got from the fins. So instead of adiabatic tip. So assuming adiabatic, sorry, adiabatic tip fins, we know the formula for Q fin as under root HPKA into I think tan HML, right? 1 second, I'll just confirm. Yeah, tan HML hyperbolic ML and the base theta b, temperature difference. Now here this is for single fin. Remember that we need to calculate m. M is nothing but HP by Ka. Here also you can assume that the thickness is negligible than the length of the fin or width of the fin. So in that case, the formula simplifies to 2T by sorry, I think 2H by KT. Yeah. Two H by KT. And if you do that, you should get M value as 47.14 per meter. So it's an inverse length unit. Okay. Perimeter of the fin will be perimeter will be 2 into the length of the fin in that direction plus thickness. So that will be perimeter. You can calculate those. And what else do you need? Cross-sectional area will be again uh, the thickness of the fin into L. So that is why LL gets cancelled in the M. And you can do this calculation and put the things in the tan HML formula. But note that the ML here, okay, yeah. So we should not make mistake here. So this L is not the total length. This is fin length. So I mean, this is your L, right? Whichever you are using as 1. This number L, which is here, we are using it as 1. So yeah, that is L, but in the fin tan HML formula, this will be your LF. So make sure that you don't commit that mistake here. And when you put the all values here, and you have to multiply by number of fins also, because this is for n fins, which are n is 8 given in the question. So when you do this, uh, you get Q fin as 26 point, sorry, 22.616 theta b. So Q total with fins is nothing but 20.07 theta b plus 22.616 theta b. So you can refer to equation number 2 here. So that is nothing but 42.686 into theta b. Therefore, how much increase that we got from increase in Q due to fins is 42.686 minus 20.97. 20.97 theta b was your initial Q without fins. So that's why we are taking it as the reference. So that is 103.56%. So basically, almost more, double with the addition of this only 8 fins on the angular annular 8 fins. This is your answer. So this type of questions are typically asked. These are like the most difficult questions that you will encounter from the fins. And there is like small part is there, some tricky type of questions. So what they typically do is they will tell you that there is a heat source. Okay, let's say no, we should use some space. So they will say that there is a fin or extended surface here, and it will be something like this. This will be at some higher temperature, let's say 100 degrees. This will be at, let's say, okay, again 100 degrees Celsius. Case 1 is this one, and your T infinity will be around 30 degrees Celsius, normal thing. So basically your heat loss is taking place from this. So this is your fin. What they ask is uh, what is the heat loss from fin. So basically Q fin, that we have those formulas, right? But here the thing is, they'll not first of all call it fin. I'm here calling it for ease of understanding, but they'll call it something else. They may call it as some extended surface or something like that. But it's effectively a fin only. So only the boundary conditions are different here. So instead of, so if you assume this is this or this as your base, and this is your tip, this part. So your tip is not like adiabatic or exposed to ambient, right? Or you know, so it is at fixed temperature of 100 degrees Celsius. So in this case, how will you calculate? So this, in this case, the trick is if you plot, let's say, temperature along this fin length, what you will observe, let's say this is your L equal to 0 and L equal to, or x equal to 0 and x equal to some L. What you will observe is the temperature will decrease from 0 and again go back to, decrease from 100 and again go back to 100, because you have to satisfy the boundary conditions, right? So basically it will be symmetric temperature distribution along the fin, and it has to be, otherwise it will not satisfy the boundary condition. So this is symmetric, like don't go with my geometry drawing. Symmetrical distribution, and at midpoint your dt by dx will be 0, because it has to be, right? Otherwise the temperatures won't match and it won't change. So basically in this part the temperature is decreasing and then it has to increase, so there will be a point at which the slope will become 0. Here the slope will be negative and here the slope will be positive. So there will be a point which is given by this center point here, where the slope will be 0. So you treat this fin as uh, two fins of L by 2 length with adiabatic tip. Okay, I mean there is a like big formula for this in terms of sine HR, sine hyperbolic, cos hyperbolic, which I also don't remember. You may go to the previous class notes and there will be given, or maybe any good book will have it. But this is the easiest way to do this. So what you do is, you know that at some point the temperature slope should change, then only it will satisfy both the boundary conditions. And in this case, since the base temperature is 100 and the other tip temperature is also 100, the slope will change at the midpoint, exactly at the midpoint. So you can consider this fin as two fins of half length. So basically what you do, you cut this fin in half, and you take this half as your one fin and this half is your other fin. And since dt by dx is 0 at the center, you assume them as adiabatic tips and you calculate. And you have to take x as, I mean length as the half of the total length, and you multiply by 2. because there are two fins. Now the next thing is, what if the base temperature is different? So the point is, let's say the same thing. Let's say you have same problem, but instead of 100 degrees Celsius here, it is at, let's say, 50 degrees Celsius. So your tip is not at exactly the uh, you know so here your tip is not exactly at same temperature as the previous case. So in this case, if you want to see the temperature distribution between the fin length, you'll observe that the temperature will decrease from 100 and it will increase. And so if this is your midpoint, so somewhere here your slope will start to increase again. So it will be something like this. So this will be your 100 degrees Celsius. This will be the point, and this is your 50 back, and this will be the point where dt by dx will be 0. So here the slope will not change exactly at the midpoint. It will be somewhere on the second half, because you know, I mean, you understand, right? Because the heat is, how should I say? Because here the heat is being lost from 100 to 30. Here it is lost from 50 to 30. So here delta T is around 70. Here delta T is around 20. So here more delta T is there. So to have same drop, you'll need more length. Here to have same drop, you'll need less length. That's the whole argument. And you need to find this length. I mean, whatever you take, any side, you need to find this length. And how to find? You need to assume some variable. Let's say you assume this as L1 or small l. So this part will be this. Sorry, this part will be your capital L minus small l, and this is the point where dt by dx. Now the small l is the unknown. So what you have is, you have this formula, t minus t infinity divided by t minus t infinity is nothing but cos h m l minus x by cos h m l. I should write capital L here, otherwise it's confusing. So this is for fin with adiabatic tip, and uh, this thing. What do you say? Yeah, adiabatic fin tip formula with length L. So temperature distribution is given by this formula, and then you can take, you can do one thing. You can take temperature gradient, or multiply this, then you'll get Tb minus T infinity here. This cos HML at the bottom will be your constant, so this won't get affected. And you'll get sine HML minus X, and you will have one uh, minus M into multiplication somewhere. So now what you need to do is, you have one unknown, right? So maybe you can use this condition, make this as 0. But if you do that, yeah, let me think. Yeah, so basically you have one equation for temperature, one equation for temperature gradient, right? And you know that at this point, that and you, you know you can use uh, you have to actually do some manipulation here, because uh, you know you can assume one fin of this much length, where your dt by dx becomes 0, and then you try to make this 0 and get one equation for small l. Then what you do, you assume another fin with base temperature of 50, ambient temperature of 30, and this much length with insulated tip, and you use this length in this formula, and you make it this 0, and you get another equation. And then from both the equations you equate, because they are equal to 0, right? So both the equations will be same, and there you have this one unknown L, which you find there, and then you can solve the next part. Once you know the L, the other things are easy, because then you know at what point you have to assume two separate fins. You know, so that way you have to do this case. I hope I'm not going into detail, because we will not have that much time here. But I hope the trick you are getting. Okay. So now I think fins. Yeah, one more problem was there for fins. I'll just see if I can find it quickly. Uh, but I think we should take it after this thing, Biot number discussion. Okay, so we'll go to the lumped part first. Lumped heat conduction. So, as discussed in the class, this bio number, which is nothing but h characteristic length divided by k of solid. I would advise you to remember this formula this way. Typically, people just remember it as HL by K, but later we'll encounter Nusselt number, which has exactly same formula, but only this K solid. Instead of K solid, there it will be K fluid. So, to avoid the confusion, just remember it as K solid. It should be less than 0.1, I think. So, like that. The 0.1 is not exactly strict criteria. It can be less than 1 also. So, I should not say. I should just say. Uh, Okay, less than 1 should be good enough. So in this problem, sir has already told you how to calculate the temperature distribution. It's not that difficult. Uh, so basically what you do is minus mcp delta t equal to ha t minus t infinity. Yeah, before that, this characteristic length scale here, we consider it as volume divided by surface area. So for sphere, volume is 4 by 3 pi r cube. Surface area is 4 pi r square. Therefore, your characteristic length becomes 4 pi get cancelled, r by 3. Okay. So yeah, similarly you can do it for cylinder, cube, whichever you want. And yeah, regarding the derivation, there is one thing that you should also know, apart from the temperature variation, is the how you calculate the heat from, let's say, 0 to t, how much heat is lost. So basically you start with minus mcp dt by dt, and yeah, this is like, since you assume the Biot number to be small, you can assume the internal conduction resistance of the body will be negligible as compared to the convection resistance, and you assume the whole body at some temperature T. So basically, your T is only function of time, and it's not the function of x, y, or z. So basically, it's not a spatial function. It's only a time-dependent temperature variation problem. And you equate it to the HA T minus T infinity. This comes from energy balance. And then you write M as rho V, and then you basically get something like uh, dt by T minus T infinity as minus HA dt rho V Cp. Then you integrate, and then you end up with some logarithmic scale, and finally you get T by T minus T infinity as T0, which is the initial temperature of the body, T infinity is the bulk temperature, and you end up with some exponential function of this sort, minus HA rho V Cp into T. Note that this is again equal to uh, exponential minus Biot number, and there is something called as Fourier number. So Biot number, so we know HL by K, but there is this Fourier number which is called as relative time also. Uh, it is nothing but alpha T by LC square. So this is your Fourier number. This is not typically asked, but there was one gate problem, I think recently only, not long back, where they they asked this problem. So if you knew by Fourier number definition or what it represents, uh, then you could have solved it. Otherwise, if you would not, if you would have known the similarity solution thing, then also you could have solved it. But if you don't know, then you can't. We'll take that problem. But basically, Biot number is the non. So basically, uh, the Fourier number represents the time part, or the variation temperature due to maybe specifically due to time. The Biot number is material properties and the system property. Fourier number also is material property, but it has time. So if any question is there in which you have to compare times, you should compare Fourier numbers. We'll take one problem regarding this, but you should know. So yeah, and the other thing that is there. So this formula everybody knows. Uh, yeah, then other thing that you should know is something called as time constant. It's nothing but what is there in the multiplication to the time term in the temperature formula. So it will be nothing but rho VCP by HA. And it will have the units of time. So basically your T minus T infinity, T0 minus T infinity, you can directly write it as minus T by tau. And you should note that smaller tau represents faster steady state achievement. So basically, and this tau is nothing but when you are, you know, okay, I put it properly. So at time t equal to tau, your t minus t infinity from this formula here itself it becomes t0 minus t infinity into e to the power minus 1. So e is 1.27. So if you do that, 1 divided by 1.27, 1 divided by E, you get 0.368. So when you say that the time constant has reached 1, or the time has reached one time constant unit, that means the temperature difference between the body temperature and surrounding is 36% of the initial delta T, maximum delta T. So that is the definition of time constant. But from question's point of view, you should remember that smaller the time constant, better it is. And why so? Because let's say you have the classic example is of thermocouples. Thermocouples are instruments that are used to measure temperature in any experiment setup. So basically, thermocouple will have two wires of different materials, and they will be welded together at the end, which is called as bead of the thermocouple. So typically, we treat it as spherical small particle, or whatever you want to call it, but we treat it as spherical shape, and its dimension is very small. So there, if you calculate Biot number, it will be less than 1. Typically, it's like that only. So therefore, there the thermocouple is the classic case where you apply lumped. Uh, One second. Yeah. So thermocouple is the classical case where you need lumped analysis because Biot number is typically less than 1, and it's a spherical shaped bead that is inserted any flow or anywhere. So there the time constant of thermocouple is usually specified, and typically what people or what the practice is that when time reaches 3 units of time constant, then you can assume that the bead of the thermocouple is giving steady state temperature of the surrounding flow. So faster the time constant, better it is, because you will not have to wait for long to take the readings in the experimental setup. So that is the basic point of it. So now we'll take some problems. And yeah, second thing is, uh, you know, the second application is quenching. So basically, you have very hot metal ball, quenching or annealing or any heat treatment process where you increase the temperature and you suddenly quench it by putting it in some cold temperature bath. There also typically Biot number comes out to be less than 1 or small value, and people typically use the lumped capacitance analysis. We can take one problem from each, but you should know that these two cases are where these things are important. So we'll take one problem of, let's say, before moving that, sorry, I forgot. Uh, you need to calculate the energy released from the body, right? So basically, what you do, you take the temperature derivative with respect to time. So basically, you divide equation number 1 with you differentiate equation number 1. So what you end up with is uh, T naught minus T infinity and exponential minus T by tau into uh, minus 1 by tau. So this is your derivative, right? And instantaneous heat transfer from hot body to surroundings is given as, let's say, Q minus K A dt by dx, right? Or in this case, we are considering time, right? So instead of that, you can just write it mcp dt by dt. So now you have this, then you have mcp, you can write it as rho vcp, rho v the volume, and then you can get instantaneous heat transfer, and the total heat transferred from body to surroundings will be nothing but the integration of q dt from 0 to some time, uh, whatever time you want to take it. We'll put capital T, let's say, but capital T represents the temperature, so we'll put T prime. So that is your final time, till what time you want to calculate that. And if you do the calculations, I'm not going into detail, but it should not be that difficult. This is your Q. It comes out to be rho VCP T naught minus T infinity into e to the power minus Biot number by Fourier number minus 1. See, this part is nothing but your MCP delta T, right? So instead of, I mean, in addition to that, you have this additional factor that comes because of the, what do you say? Because of the this thing, uh, because of the heat conduction from the body. So what happens when your yeah, so I'm just thinking T dash is very large. In that case, what happens? So Biot number is constant, alpha TLC square. So Fourier numbers reaches very high value. Then e to the power minus very high. So that is basically 1 by e to the power very high. So that is almost 0. So that will become minus 1. Yeah, so in that limit, I think you have to take limit here. But okay, for here I should mention in time t dash. So we should remember that. So that is one thing. Now we can take some problems. So okay, so this is a thermocouple problem. So there is a pipe in which some gas flows and one thermocouple is inserted with spherical bead, and diameter of the bead is 0.706 mm. And okay, I'll write all properties directly here. Thermal conductivity is around 20, so typically it is, I think, steel. Cp, or in this case it's only C because it's, I mean, I should not have written Cp everywhere, but you get the point, right? It's Cp. I mean, it's in case of solid, Cp is equal to C only. So we'll continue with the same notation. Let's say Cp as 400 joule per kg Kelvin. Yeah, so it looks like some alloy of steel, some other grade or something. Rho is 8500 kg per meter cube. These are the properties of thermocouple material and bead. Here in the stream, the H is given as 400 watt per meter square Kelvin. This is the heat transfer coefficient. And T infinity is 300, so it's a hot gas. which we are measuring the temperature of. Now, if initial temperature of the thermocouple is 30 degrees Celsius, what is the time taken by the bead of the thermocouple, which is this spherical part, by the bead to reach 298 degrees Celsius. So this is your question. Okay, so now we can directly use the formula. So 298 will be your T. T infinity is your 300. Initial temperature of the bead was 30. T infinity is 300. This will be your exponential minus HA. H is 400. Now it's a spherical bead, right? So as we talked about it, the LC, the characteristic length. Oh, sorry, my bad. Before doing all this, you should check the Biot number. So Biot, some people call it bio number, some people call it Biot number. It's okay. So LC in case of sphere is R by 3, as we discussed earlier. So that is D by 6. So HD by 6K. H is 400. Diameter is 0.706 into 10 to the power minus 3 meters. 6 into 20. These are the given values. So Biot number comes out to be 0.0023, which is less than 1, significantly less than 1. So therefore lumped system analysis is valid here. And then you use the temperature formula. So now your temperature, you need to reach 298 in the ambient temperature of 300 with initial temperature of 30. That will be minus H A T by rho V Cp. So you will have 6 into H, which is 400, divided by rho 8500. Cp is, I think, 500, 400 into D, 0.706 into 10 to the power minus 3, and into time. So one equation, one unknown, and if you solve this, you should get T or time around 4.9 seconds. So this is your answer. Okay. Like mostly in some, like most of the exams, typically they will ask time only, and if you want to ask, let's say, time constant, they can ask what is the time constant for this thermocouple. So you can do that, rho VCP by HA, and that V by A you replace with by D by 6. So then you will get the time constant. So you see, it needs almost 5 seconds to get heated from 30 to 298, right? So if you take any reading between initial 5 seconds, that will be wrong reading, because it will have the temperature variation of thermocouple bead itself. So typically you should wait for 5-10 seconds and then take the reading. That is the correct way to take the readings. Okay, then yeah, one more question, which is like slight variation of the things that we are studying so far. So there is a oil bath. So bath means it's like a chamber, and they one ball of copper is dropped in it. So this is your oil bath. It is at temperature 300 Kelvin, and it's dropped. So basically, it is moving in this direction, and it's a copper ball. So it's a copper ball with diameter 5 mm. Thermal conductivity of copper is pretty high, 400 watt per meter Kelvin. Density is 9000 kg per meter cube. And the heat transfer coefficient is given as 250 watt per meter square. And here it is mentioned that assuming lumped analysis to be valid, calculate the fall or rate of temperature change of the ball at the beginning of cooling. So as soon as it is dropped, they want to know what is the rate of change of ball. So here they have mentioned that the lumped analysis is valid, so no need to calculate Biot number. But even if you do, it should be fairly less than 1 only. So in this case now, you have to do that thing. Since they are asking for temperature gradient, you have to take dt by dt, and which we did some time back. So basically, it will come out to be HA rho V Cp, and the T0 minus T infinity term will be there. Minus sign will be there. Then there is this exponential term minus HAT by rho V Cp. Okay, so this is just differentiating the temperature distribution expression. So now they are asking what is the dt by dt at t equal to 0, right? So when you put t equal to 0, this term will go to 1, and therefore whatever we will have minus h a rho v cp t0 minus t infinity. And if you again, it's a spherical ball, so v by a will be again d by 6. If you put those things in this, you'll get minus 17.31 Kelvin per second. So within a second, the ball temperature is, dropping by this much rate initially. Later, the rate will be decreased because the delta T between the bath temperature and ball temperature will decrease. So that will reduce the delta T will reduce the rate of change of temperature fall also. So this is one thing. Let me see if there is any another interesting thing is there. Sometimes instead of ball they will give you cube. So in cube volume is a cube and surface area is 6a. So there it will become 6a square. So there it will become a by 6. A is the side of the cube. Yeah, there is this question. 1 second. Uh, what is it? 1 second. There was one question which combines fins and this guy, this lump analysis. Not combined, but Bayes number is. Sometimes you'll see some questions, you know, which are like that. So I just want to take that. Give me some time. It was somewhere here only. Yeah. So yeah, this type of unusual question was asked some time back. I think engineering services exam prelims. So the question is: a fin will be more effective when bio number is. So it was a MCQ type of question. First option was greater than 1. Second option was equal to 1. Third option was between this range. And fourth option was less than 1. So prima facie it looks like some absurd question which we don't you know understand why this is related with the fin. So basically you should follow this line of answering. So Bayes number for anything, even if it is fin, it will be HLC by K, K of fin. So LC will be the characteristic length for fin. So that you leave it. It's just the length, some length dimension. So that is there. And regarding the fin effectiveness, we know that fin effectiveness, if you remember last class, for typical, if nothing is mentioned, we assume it is at adiabatic or long fin, and in this case, you get some measure for effectiveness in terms of this formula, which is Km by H. So if you do that, typically you assume it as a long fin, and then this tan HML, etc., terms go away. So then you put m as under root hp by ka, and then if you simplify, you get something like kp by ha. This is from previous class, this formula directly I'm borrowing it. So now that is there. So the question is saying a fin will be more effective. So fin is more effective when its effectiveness is high, correct? So now once the fin is fixed, or once the fin is designed, you cannot change its P and A, right? So this P by A, that is the material or the construction property. Once the fin is finished, you cannot change P or A because that is the fixed quantity. So to have high effectiveness of fin, this K by H ratio should be high, correct? From this expression, effectiveness expression. And if you look at the Bayes number, uh, but Bayes number is proportional to h by k. So basically, uh, you know, from here you can see if you want k by h to be high, then h by k will be minimum or less. So that means, therefore, to have high effectiveness for a fin, Biot number will be lesser. So that is the only conclusion that you can draw. How much less, what should be the value, you can't say anything with this data. For that, there should be more data which is not given in the question. So therefore, uh, Biot number less than 1 will result in higher fin effectiveness, because that's the only option that makes sense, right? Otherwise, all other options are uh, different on the other side. So this is the correct answer. Last option, fourth option. So that is there. Yeah, and coming back to one question that was asked in, I think, GATE exam. Yeah, so some of you might have seen that, but let's go there. So yeah, what the question was, I think it was 2016 mechanical. Yeah. So in the question it is mentioned that there are two cylindrical shafts, okay, A and B, and yeah, I think their lengths are same, only their diameter is different. Yeah, so like there are two uh, shafts of same length, and same material as well. So this is shaft A. Actually, I drawn the bigger shaft later, so otherwise it was reverse in the question. So the diameter is 0.4 meter for this shaft. Diameter is 0.1 meter for this shaft. They are of same material, okay? Sorry, not same material. My bad. K is 40 watt per meter square for this guy, and K is 20 watt per meter square for this shaft. Volumetric heat capacity is given, so that is basically, what should I say? It's not CP, it's, I think, rho CP. Joule per kg Kelvin. Yeah. So rho CP is directly given for this shaft B. It is 2 into 10 to the power 7, I think. Yeah. 2 into 10 to the power 7. The units will be joule per meter cube Kelvin. For this rod, it will be 2 into 10 to the power 6 joule per meter cube Kelvin. Huh. And both of these shafts are introduced in a furnace, which is at, you know, uh, furnace temperature is also not mentioned here. Yeah, so what they are mentioning is that for both the rods, initially they were at the same temperature, and they, at the same time, they both of them are put in the furnace, and at all times, surface temperature of the shafts is equal to furnace temperature. That's it. They have not mentioned anything. Any value is not mentioned. Uh, so what they are saying is, question or the center line temperature of shaft A reaches 400 degrees Celsius in 2 hours. How much time will be required for center line temperature of shaft B to attain 400 degrees Celsius? Neglect axial conduction. So, you know, they are just saying that it's a radial conduction problem. There is no axial conduction, and you have to. So basically, uh, this center line will be this, right? So the shaft A, which is the uh, thicker shaft, reaches its center line reaches 400 degrees Celsius in 2 hours. So what about the shaft B? When its center line will reach the uh, temperature of 400 degrees Celsius? There are two ways to solve this question. I mean, initially I could not solve it, but because at that time I did not know all this. But later I found out there are two ways. You can solve it since there is a mention of time. So and it's a 1D problem, 1D radial heat conduction. So in that case, you can take the help of Fourier number, because in 1D heat conduction, only Fourier number is there, which talks about time. Otherwise, all other numbers are they don't talk about time basically. In conduction, that too in 1D. So you may ask that what about the Biot number, etc. Nothing is mentioned here, so we can't say anything about Biot number. And Biot number, anyway, it doesn't give any information about time. That is one thing. Second thing is, the second way to approach it is using the similarity solution. So basically, the idea is, uh, in this shaft, what is happening is the heat is being conducted from the furnace. The heat is being convected from the furnace to the shaft temperature, and from shaft temperature, it is conducted to the inside of the shaft. So and that is mostly 1D, because axial heat conduction is negligible. And therefore, if you go to your governor equation, that is K uh, dt square by del x square is nothing but rho Cp del T by del T. Because there is no heat generation, so that Q dot term will not come. And since it's a 1D problem, we'll assume the radial direction to be x direction. So if you do the simple scaling, uh, so this K and this some delta T will be there. Your x will be your diameter, because that is the radial direction. So here you'll get some diameter or some radius you can put. That doesn't matter, but some length scale which will be second derivative, so d square. I should not say equal, because we are doing here it is equal, sorry, and here we are doing some order of magnitude analysis, so here it will be approximately similar scale. And here your order of delta t will be same, because delta t is the delta t. And here you will have some time scale. So you can, this delta t term will get cancelled. So what you are left with is, if you want to get some idea about time, essentially scales as rho Cp d square by k. There will be some proportionality constant, but we don't care because we don't want to see. We just want to compare A and B, right? So we can use approximate, or not approximate, but without exact constant also we can go do away. And if you know the definition of alpha, which is thermal diffusivity, it is K by rho Cp. So the alpha will come at down. So like that. So you can use this analogy as well to solve this problem. And you know that, yeah. So this is one way. This is from the basics. Second thing is, let's say you don't know this way, scaling, etc. Fourier number, if you know, then also you can do, because that is the only time uh, connecting parameter, right? So Fourier number, since they are, initial temperature is same, material is different, but uh, you know, we don't have anything to go on. So only thing that we can uh, conclude is that Fourier number should be scaling or equal. Okay, so because see, this Fourier number comes in exponential power, right? Exponential something. So uh, and that determines the temperature. Some temperature term is proportional to some exponential term, power, Biot number, and Fourier number. Biot number you can't do anything because h is not given, so we assume it is to be same. So actually we can't assume anything because h can be different because the size is also different. So only Fourier number you can assume to be equal. So here also the same thing you will end up with. So Fourier number is alpha t by some LC square. So LC characteristic length, you can take it as diameter for A, and alpha t, or exact equal you can't write actually. You can say they'll be specific, more or less same. So if you do that, you will also end up with the same scaling which we end up here. So both way you can do it. So therefore, if TA by TB you want, it will be dA by dB square and alpha B by alpha A. Okay. Yeah. So now what is all that is given? Acha, A reaches 400 in 2 hours. So TA is 2 hours. TB is unknown. Diameter of A is 4.4 and diameter of B is 0.1. Alpha B, K by rho Cp of B. So K by rho Cp of B. So 20 divided by 2 into 10 to the power 7, and that alpha A I am writing ulta. So K by rho Cp for A is 2 into 10 to the power 6 and 40. Okay. So now many things will get cancelled. This 2 will go away. This 2 will come here, and there will be 110 here. So this becomes 120, and this is 4. So this becomes 16, and this is 1 by 20. So this is 4 by 5. So TB will be nothing but 40 by 16 into 40 by 16 only. So this is 10 by 4, 2.5 hours. Let me just check the answer once. Yeah, so I mean here it looks pretty easy, but I know this question when it was asked in the exam. Not many could solve this. It was not actually typical question from this part. So that's why. Anyway, so I think we have two I mean other topics that were there, but see that similarity solution thing that we can cover later as well. I feel maybe in boundary layer it will be there somewhere, but essentially similarity solution. Uh, you should remember two things about it. When do we use similarity solution? That is the first question. Typically, it is used when one of your dimensions in your problem is infinite. So, in the class that we talked about, uh, uh, one direction is infinite, semi-infinite case, right? So, you have to use similarity solution. And why do we use it? That is the second question. The answer is in similarity solution, what you do, actually, it basically, I think it was Blasius. He used similarity or gave similarity solution for boundary layer, hydrodynamic boundary layer over flat plate. And there also in boundary layer, we'll talk about it later. But if you know boundary layer also one dimension which is perpendicular to the plate or flow direction is typically not bounded. It can go, it can change, and it's not actually fixed. It's not infinite also, but it's not. It's continuously varying. So there, what you do. So yeah, basically similarity use when your one of your dimension is not bounded. So there, Blasius gave the similarity solution, but it is used in all many problems. So that is first thing. And what happens in similarity? You combine two variables in one variable. So what happens? Uh, your complexity of the problem reduces governing equation, because now it becomes typically it becomes function of single variable or at the max two variable. So basically order of the uh, not order, you should say the number of unknowns reduced by one if you use similarity solution. And there are certain rules that the similarity variable should abide by. I mean, otherwise you can't use any random similarity solution. Typically, the valid similarity solution will result in uh, the reduction of one unknown variable, and boundary conditions should be satisfied. Otherwise, that similarity solution is not valid. Similarity variable is not valid, and in the end, typically you end up with the governing equation of some sort of ODE, PD, linear, non-linear. It can be anything, and you typically need uh, uh, you know numerical methods to solve those equations. So typically, analytical solutions for such similarity variable methodologies are not common. There can be one or two, but typically at the end you have to take the help of numerical methods to solve those ODE or PD. So that is the main thing about similarity solutions, or in this case related to the 1D infinite, semi-infinite case heat conduction problem. I think we will encounter it later also, so that's why I'm not focusing much here. The other thing that is there is 2D heat conduction. So 2D heat conduction is important problem, yeah, because we use first of all, I mean there are cases in 2D heat conduction also. One is steady state 2D heat conduction, and another is unsteady state 2D heat conduction. But I think in this course we are studying only 2D heat conduction, and that too in Cartesian coordinates. It can be in spherical or cylindrical coordinates. So typically, uh, those are like complicated solutions. Bessel functions, Legendre polynomials, etc. Uh, come there. But coming to the scope of this course, 2D heat conduction in steady state and in Cartesian coordinate system is the scope of the course. So basically, I'll explain the because I saw one problem in your assignment also. See, uh, 2D steady state heat conduction Cartesian system, and I think the heat generation is zero. You can take heat generation, but then I don't know. I mean, the separation of variable method will not be the correct one. I think you have to go for some different method there. But coming to the simple one, I should not say simple. It's not simple actually. But yeah, the point is, one second. So typically you'll have something like this, and you will be your 2D. This will be your 2D domain. Some temperature T0. So you consider this X direction and this is your Y direction. Uh, Typically, what you do is uh, uh, one second. I'll just draw the complete figure. Lx and this is your Ly, and this will be your temperature boundary conditions of these two walls. This is a general formulation. It will change as per your. I mean, it can change, but typically what happens, there will be a one homogeneous direction. What I mean by homogeneous is the temperature will be same in this direction, and there will be one inhomogeneous direction, that will be this direction. In your assignment, this temperature is same as these two. So when you don't dimensionalize it, it all becomes 0, and this becomes 1. But typically, one direction is homogeneous. You can keep these also non-homogeneous. That means some TC or TD will be there, which are not same. But in that case, the solution slightly becomes tedious, because when you don't dimensionalize it, you will not have uh, homogeneous boundary conditions. You'll have inhomogeneous boundary conditions, and it may not be possible to solve them analytically. But yeah, coming back to the scope of this course, so I'll not spend much time on the separation of variable thing, because it's typically straightforward. This is your governing equation, and you put uh, t as some function of x and y, and you assume that they are independent, because this is a linear sort of governing equation. And then what you do, how should I say, yeah, you non-dimensionalize your temperature basically. So uh, okay, boundary conditions will maybe write them later uh, when you are going to solve it. So basically what you do, you put this back in your governing equation here, and you separate the variables, and what you observe is uh, you'll get something like 1 by capital X del square x by small x square plus 1 by capital Y del square y by small y square equal to 0. I mean, in class it was different variables, different functions. I'm taking xy, capital Xy, uh, but it usually follows the same separation of variable method, whatever function you choose. And one thing that you should notice, uh, wherever you have homogeneous boundary condition, for example, this boundary condition, typically you equate that. So basically, what you write here is 1 by x del square del small x square will be equal to some constant lambda square, and 1 by y del square y by del y square as some another constant of same magnitude but opposite sign, and lambda is greater than 0. Positive. Or you can't say that actually. Let's say that's why we are taking square, so that's when they become same. So this is the case. But one can argue that can I put, I mean, this side as lambda square and this side as minus lambda square? No, you can't, because if you do that, let's say if you put this side as the positive constant, then you get x as the solution, which is a to the power e alpha x plus b e to the power minus okay, so not alpha, lambda actually, sorry. And this solution cannot satisfy these boundary conditions, because this is an exponential function and it cannot come back to 0 at 2 points in non-dimensionalized form. So this has to be a sinusoidal function, and that is only possible when you take this as negative. And if you take that, you end up with some sinusoidal form of function, which is a sin lambda x plus b cos lambda x. Yeah, so this sinusoidal function can satisfy these boundary conditions. That is possible. Exponential function can't, because exponential function will either go like this or like that, something like that, but it cannot go like this, right? That is only possible with some combination of sinusoidal functions. So therefore you take that, and therefore you end up with now you take boundary conditions. This is a general method, okay? I'll tell you where the difference comes, because governing equation, solution methodology, they are more or less same, but only the boundary conditions will cause the change in the formulation or the solution. So what happens here, at x equal to 0. So x equal to 0 is basically your y-axis. One second. So basically one of this a and b goes to 0. That's what happens. Okay, so before going there, what you typically do is you non-dimensionalize the temperature. So what I mean by that is you put some t star as t minus t naught. So in that case, t star is 0 here, t star is 0 here, t star will be tb minus t0, and here the non-dimensionalized number will be ta minus t0. It's just the way of writing, because now this becomes 0, right? So this makes our life easy. So we know at x equal to 0 and y equal to 0, your t star is 0. And since we are talking about x only here, this implies your x will be 0. And that is possible only if b is equal to 0, because sin pi anyway will go to 0. So this term goes away. And then at x equal to Lx, y equal to 0, you have t star again equal to 0. Correct? So therefore, because we are only considering x now, y will consider later. So t star is 0, that means capital X has to be 0 there. Capital Y we cannot say in this boundary condition. And therefore your sin lambda x has to be 0, and that gives you lambda as so that this will be Lx, sin lambda Lx equal to 0, and that will give you n pi by Lx. So this is what they call eigenvalues, and this n will be starting from 1, not 0, because otherwise it's a trivial solution. Okay, so this much is same in class also, and in your assignment also you can apply same logic uh, with some proper modifications, but till this point everything is same. So basically your x function is, which is a function of only x coordinate, it is n a sine n pi x by lx. This much is there. Now you put you take this guy. This is 1 by y d square y by dy square is some positive constant that gives you y as a exponential lambda y plus b exponential minus lambda y. Now here you have to put boundary conditions. uh, but before that you write the whole uh, expression for t star, no? Let's say you'll put some t star, so it doesn't matter because anyway we are scaling everything, right? So your t star will nothing but become, which is non-dimensionalized temperature, which is xx into yy, will become sine n pi x by lx, and then there will be this whole term coming. Okay. It will be this multiplied by sine n pi x by lx. Okay, and some constant that will be actually subsumed. No need to write it up separately. But and you can write lambda as n pi by lx here also, n pi y by lx, and here also minus n pi y by lx. But this n can vary from multiple things, right? So the complete solution will be summation of these all n's because it's a linear combination of x and y, right? So this will be your t star. So now there are two unknowns, which are these. So till this point it's all same. It will remain same only because uh, the boundary conditions only will cause change hereafter. So now you have to find these two constants, and that is where it becomes tricky. Uh, and what do I mean by tricky? So we use another boundary condition that at y is equal to 0 and x equal to 0, the bottom boundary, you have T star as Tb minus T0. This is your non-dimensional temperature at that boundary. So now you put this into equation 1. So therefore equation 1 becomes something like this. Tb minus T0, this will be your T star, summation of n equal to 1 to infinity an plus bn, because y is 0, so exponential terms will go to 1, sine n pi x by lx. X cannot be 0, sorry. I mean, that is origin only. Here also I should not say that way. Uh, here also why you can't put it because it's origin, but we are saying boundary. So yeah, Sorry for that. So x can be anything from 0 to Lx because that's the bottom boundary, right? So now you have this one equation. Now here is the tricky part. You have to use something called as orthogonality relation, which is given as this. You can solve this. It's basically integration only. Lx sine m pi x Lx will be Lx by 2 into some function, and this function is equal to 0 if m is not equal to n, and equal to 1 if m is equal to n. They call it what they call this function as Einstein's Kronecker delta, I think, something like that. So this is the tricky part, that you have to use this equation here. Sorry. Yeah. So this is called as orthogonality relation. So what you do, you multiply equation 2 by sine pi x on both sides. So what you end up with is you'll end up with something like that, 0 to Lx. Yeah, it should be Lx only. Dx dv minus d0 sine m pi x by Lx, and here you'll have summation an and bn are constant, so they'll come out of the integration side. Okay, and then this term, it becomes Lx by 2 Kronecker delta mn, and there'll be only same when m equal to n, and otherwise it will go to 0. So therefore this whole bracket reduces to Lx by 2, and here again this is constant, so it goes out of the equation. You have to integrate this sine m pi x term, and if you do that, you'll get, because we don't have time now, it's a simple algebra, you'll get something like this. So when m is even, this term is 0. When m is odd, this term is non-zero. So like that. So basically this equation you have, so there are two unknowns, am and bm, and then what you do, you do the same thing for other boundary, which is at y equal to ly, and at y equal to ly, your t star is nothing but ta minus t0. Okay, and if you do that, oh, it's 8:50 now. Okay, fast I'll do. So basically you have to do the same thing. Now what happens? This becomes ta minus t0 equal to n equal to 1 to infinity. This an e to the power n pi ly by lx plus b e to the power minus n pi ly by lx. This is your first term, and then you'll have sin n pi x by lx This is your usual second term. And then again you multiply both sides with sine pi mx, and then what you end up with is, I'm skipping one step here, but I think you can get it as done previously. It's same thing only. But here you end up with am expon e to the power m pi ly lx plus bm e to the power minus m pi ly by lx into lx by 2. Okay, so now equation 3 and 4, if you observe, there are two unknowns and two equations. So now you have to use your algebra knowledge and you have to get the values of am and bm. And once you get them, you know the T star variation formula, right? So here this n subscript will become m now. One second. Okay, because m is just a subscript. I mean, it can be n or anything, right? So once you get a and bm from these 3 and 4, you have solved your problem, and you put back that in T star uh, relation, which is here. So I'm just saying, when you find a and bm, put them here. But you may say that it is a and bn, right? So what? It doesn't matter. You just change this index as m equal to 1 to infinity, and then you should be fine, I think. One second. Am I correct or just wrong? Mm, yeah, I think you should be fine. Don't put it. Don't change the index there. But I think, see, you'll get some constant, right? Yeah. So that is function of m. Yeah, I think you have to change the index there. But anyway, somebody will solve this. Coming back to your assignment problem, uh, in assignment, your this bottom boundary is again at 0. Uh, this is your 0. All three are at 0, and this fourth one is at 1. So what does that change? The first part remains same. In second part, where you use orthogonality, this part is equal to 0 in your case, in assignment problems case. If that is 0, then your am and bm will become am equal to minus bm. That will be equation 3. And here this t star is 1. So this is your 1. And therefore this is your, uh, so when you multiply by sine m pi x by lx, and then you integrate from 0 to ly, in that case there will be no this sorry, 0 to lx, then this is only 1, right? So it will be just sine pi m pi x by lx dx 0 to lx, something like that, into 1. So that will be cos. So I think this term will be 1 in your assignment problem. So then you can find, right, because am is equal to minus bm, and then it is this lx will go, this 2 will come somewhere here, and then you can simplify and get your answer. I think that should be okay. Okay, so I think we have overshoot. So I will stop now, and hopefully see you in the next class.